So first of all, congratulations to everybody for answering these questions and not being distracted by the fact that in this paper, more than many of the other papers you were reading, there's a lot of detail that you might regard as a little bit extraneous, a lot of genetic terminology and jargon. But judging from the answers, it looks like most people really recognize this for what it is. It's essentially a fairly conventional application of conventional epidemiologic methods to the problem of discovering genetic variants that are associated with breast cancer. So the first question I asked, why do we insist on very small p-values in genome-wide association studies? So I've actually pulled a couple of answers off the discussion board and lightly edited them. So Monic G says that p-values need to be reduced due to the large number of tests conducted on individual SNPs across the genome, and essentially points out that if we were just dealing with one SNP and did a single statistical test at the 0.05 level, then we would probably be entitled to test at that level. But because we're testing this very, very large number of SNPs, if we tested them all at the 5% level, then we'd have 25,000 or more associations that we would declare as p less than 0.05, just purely due to chance. So we can't tolerate that level of false positives. What you need to know is that we think that there might really only be tens or hundreds or thousands at the most of true positives in this sort of experiment. And so that ratio of false positives to true positives is something that isn't very useful. So because we're testing so many associations, we need to substantially reduce the alpha to really try and winnow out, focus in on the small number of genetic variants that have the strongest associations, the most extreme associations, because those are the ones that are least likely to be chance results. So another student talks about something called the Bonferroni Correction, and essentially the Bonferroni Correction proposes that we don't arbitrarily pick a p-value to test against. Of course, the value of 0.05 is rather arbitrary in the first place, but we divide by the notional number of statistical tests we're doing, and that tells us the p-value, the Bonferroni p-value that we can test against. So in this case, conventionally in genome-wide association studies, the p-value we test against is 5 times 10 to the minus 8, or 5 with a lot of zeros in front of it here. And how do we generate that? Well, we divide 0.05 by a million. Where did the million come from? Why don't we use 528,173, the number of SNPs that we actually tested? Well, what you have to know is that for many of those SNPs, there are other genetic variants in the genome that are highly correlated with those SNPs. And so we're really testing a larger number of variants when we test this number of variants on the genome. And really totally arbitrarily, the community settled on a million as being that number. It's probably actually quite a bit larger number. And the community settled on this value of 5 times 10 to the minus 8 as the multiple comparisons corrected test for declaring genome-wide significance. So what value do we choose as this Bonferroni corrected p-value? Well, we divide the arbitrary standard p-value of 0.05 by the number of statistical tests we think we're doing. And in this context, we have agreed to divide by a million. Why a million rather than 528,173, the number of SNPs on the chip? Well, for that you need to know a little background genetic information, which is that for each SNP on the chip, there's often other genetic variants that are highly correlated with the marker SNP on the chip. So we're effectively testing a large number of variants, probably actually in reality many more than a million, but it was agreed that a million was a good number, and we divide 0.05 by a million. We get a lot of zeros before the 5 times 10 to the minus 8. And that is the value that we conventionally test against for so-called quote, genome-wide significance. So let's go to the next question. Why do we need very large sample sizes for genome-wide association studies? So the answer is that we're expecting actually quite weak, small relative risks, and we're also demanding this very small alpha courtesy of multiple comparisons testing. And so we need a very large sample size to have really any statistical power with these low levels of alpha. So Monique G points out that with small sample sizes and very low alpha, risk that we'll reject many associations that are in fact true, so-called type 2 error, and we mightn't have any significant SNPs at all. In fact, even with very large studies, we are almost certainly rejecting very, very large numbers of variants that are probably actually associated with the outcome if we could do a big enough study, because many of the relative risks or odds ratios that we're looking at are very, very small indeed. And the one thing we've shown in practice, the example I gave you was one of the first genome-wide association studies for breast cancer, and really only one variant was still significant after the replication phase, the FGFR2 variant. The one thing we've learned is as we increase sample size, we increase the number of variants we can detect, and as of December of 2012, there are now a little over 70 genetic variants that have been associated with breast cancer by accumulating larger and larger sample sizes. So does it matter for a disease like breast cancer that affects about 1 in 9 women in the United States that some of the controls might subsequently develop the disease? So this is a question that's generic to any prospective or case control study. Is it an issue that some of the women or men that you're calling controls might subsequently develop the disease that you're interested in? And the answer is it could matter. The question is, how much will it matter? For a very, very rare disease that is actually quite unlikely to occur maybe in any of the controls, then it stands to reason that it's not going to matter very much or hardly at all. The relative risk won't be different if none of the controls subsequently became a case, or the proportion that became a case is a very small proportion of the total number of controls. For a common disease, something like high blood pressure or diabetes, or in fact breast cancer, then it could be an issue if you're calling men or women controls who subsequently go on to become cases. There are ways of dealing with this. So in a prospective study, if we can follow people over time and analyze it as a cohort study or a nested case control study like the studies that we're talking about here, we can use incidence density sampling to deal with the fact that controls may become a case. So early during the period of follow-up, somebody may be a control, but they may actually contribute to person-user follow-up as cases if they get diagnosed later in the follow-up. The other thing that's worth pointing out is that for many age-related diseases, this potential problem is more of a problem if you're analyzing a particularly young series of cases and controls than a relatively older series of cases and controls. In relatively older people, most of the controls that were going to become cases have already become cases and should be in your case series, and a smaller fraction are at risk of subsequently becoming cases. So it's something you always have to think about, less of an issue for the rarer diseases. So the next slide, you'll have noticed in the studies that contributed to this genome-wide association study that not all of the studies initially saw the same variance as even nominally significant at the 0.05 level. And so again, a very generic question in epidemiology, not at all unique to genetic epidemiology, is why might a result observed in the first study not be observed, in other words, not replicate in subsequent studies? So actually there were a lot of answers on the discussion board, and most of them are correct, because there are many, many reasons for this. Probably the first thing you think about, particularly in this context of relatively weak odds ratios and relative risks, is the first result may have been a false positive, just due to chance or perhaps due to some bias in the study. And if you see a result that essentially never replicates or very rarely replicates in subsequent studies, then the first thing you think about is that this was just a chance false positive, or maybe due to some unique characteristics of bias in the initial study. But there are other reasons you have to be careful about. Maybe the subsequent study is less powerful. If you do a very big study and observe a relatively weak relative risk, it's not too much of a surprise that if you did a smaller, underpowered study and failed to observe that result as being statistically significant, it may just purely be due to the fact that you didn't have enough power to observe the association. The usual thing we get into discussing when we have a mix of positive and negative studies is, well, to what extent those different findings could be due to some form of selection bias, information bias, the way confounding was controlled in both the positive and negative studies. Maybe the positive results are due to some form of bias giving you the positive result. Maybe the failure to observe a true positive might be due to so-called negative confounding or some form of bias which has prevented you from observing the true positive. So this can be fodder for a lot of back and forth in reviews of the literature, trying to work out if the findings are inconsistent. To what extent is that due to chance? To what extent is that due to some form of bias? Another reason that you mightn't observe the association is that the prevalence of the exposure can vary around the world. So if you're interested in the associations of consumption of milk with a certain outcome, there are parts of the world where milk is a very rare exposure, and so you're not going to be able to observe a positive result in those parts of the world. Similarly, if you're interested in the health effects of smoking, there are still parts of the world that you can find where smoking is a rare behavior, so those aren't going to be places in which you're going to be able to do studies with a lot of power to examine the health effects of smoking. Finally, in addition to the sort of concept that you do or don't observe an association, a sort of plus-minus dichotomous outcome, the strengths of relative risk can vary. So even if you do observe the association, the degree of association or the degree of positive result can vary. And there's an interesting phenomenon, sometimes called the winner's curse, that can come into play particularly in studies where you're examining a very, very large number of associations. The associations that you declare to be positive in your initial study are going to be the associations that have the strongest effects because they need to be strong to survive multiple comparisons testing, and some of that strength may be due to a chance excess in the strength of the relative risk. And so when you go and you replicate, you may actually observe a positive association, but the relative risk may be weaker. And this is something that's been observed in a lot of genome-wide association studies. The relative risk reported in the initial study often is seen again, but is actually weaker because the first report was probably an overestimate of the true underlying association, because we're only harvesting a fraction of the true positives and we're harvesting the fraction that have the strongest effects in the initial study. So that brings us to the final question: why might a meta-analysis, a way that we can statistically summarize results from multiple studies, why might that be superior to looking at individual studies or simply generating a table from those individual studies of the numbers that are, quote, positive and the numbers that are null? And the answer here, meta-analysis of multiple studies allows for a much larger amount of data to be analyzed, thus giving us more statistical power. Also, by combining the number of those results of multiple studies, the role of random chance is reduced. And I edited this a little bit, but maybe good and bad studies may balance out a little bit. Maybe studies with a positive association due to bias or a null association due to bias may be balanced out if we put a larger number of studies into a meta-analysis. So we haven't gone to the details of how we do meta-analysis, but it's a technique essentially where you take all of the individual study-specific odds ratios and confidence intervals and generate usually a weighted summary odds ratio across all of the component odds ratios. We usually weight by the size of the study or the width of the confidence interval. So larger studies with narrower confidence intervals have more weight than smaller studies with wider confidence intervals. And so this is a technique of summarizing all of the data, at least all of the data that you can get your hands on, in a single summary estimate, which is usually a better way of summarizing data than counting the number of positive and null studies. There is one real substantial weakness to meta-analyses that needs to be acknowledged, and that is the usual way we do meta-analyses is to go to the literature, pull out all of the studies of a particular association, and then extract those odds ratios and confidence intervals so we have a summary of all of the published data. And that exposes us to an unusual form of bias called, quote, publication bias. So by definition, if you're going to the literature, you can only find the studies that were done that went on to be published. But one of the phenomena that we know to be rather pervasive is that there may be studies out there that for a variety of reasons were performed, might have been reasonably good epidemiologic study designs, but there was no positive association observed. And so either the investigators chose not to pursue this, maybe the editors and reviewers of the journals didn't think this was a very interesting result because it wasn't positive. And so sometimes these analyses can be done but never actually filter into the literature. And so in the literature, we may have a literature that's biased towards a higher proportion of positive results. And so we may overestimate the odds ratio because we can't actually access the negative results. There are a few ways that people have proposed to mitigate against this form of bias. Actually, in the clinical trials world, they've done rather well in the last 5 years or so by insisting on so-called registries of clinical trials. And there's one run by the US National Institute of Health. There's a parallel one from the World Health Organization. And for clinical trials where you're going to put people in your studies at risk of exposing them to a new drug, or where it's very important to have all of the results if you're going to make accurate statements about the effect of a new drug, we want all the data. And so now it's fairly routine for the people doing the studies to actually declare the fact that they've done these studies. So at least we have a registry of all studies that have been performed and a means of going and approaching the investigators for asking for the data so we can put together the data, whether those data are ultimately published in a journal or not. In genome-wide association studies, this is a little bit less of an issue because these studies tend to be fairly expensive, and the community tends to know who's got what data, and there's been a good ethic of data sharing, which means that by and large people are happy to contribute their data. People are also usually aware that their own individual study might be rather underpowered, and so the only way of getting the right answers is to put all the data together, but that's not to suggest that everything's perfect and that we ever have access to all the data that theoretically exists. So those are the answers to the questions I posed. Congratulations again on persevering through the genetic jargon of this particular set of examples. I hope it's given you a taste for modern genetic epidemiology, but also shown you that, in fact, this is really no more than a fairly conventional set of applications of standard epidemiologic study designs, standard biostatistical techniques to a new exposure, the exposure being the fact that we can now analyze DNA at hundreds of thousands of points through the genome and reach statistically robust answers to the question, where in the genome are there associations between genetic variants and diseases of interest. Thank you.